All right, ladies and gents, welcome back. 9.8 interval, or I'm sorry, radius and interval of convergence. So what we want to do here, all right, let me fix some stuff on my end here. Okay, so what we want to do is we want to approximate the value of a function, right, is one of the main uses of power series, right? So not all power series, though, are created equally. Some may give you pretty good approximations. Not sure why that didn't write, okay, for any value of x, while others may only give good approximations at or near the center. So what we have is what's called the radius of convergence. For a power series, will tell us how far away from the center you can be and still find a good approximation. So here are some rules for the radius of convergence. So if the radius of convergence is capital R equal to 0, then that means the series converges only at C, whatever the center is. Okay? The radius of convergence, if that is some value of R greater than 0, so some value, some finite value. Okay, so this one is finite. Such that the series converges absolutely for this and diverges for this. Okay, so that's the second step. So if the radius of convergence is finite, then such that the series converges absolutely for that and diverges. The number 3 there, if the radius of convergence is infinity, that means the series converges absolutely for all values of x. So in the second scenario where r is finite, the interval may have open or closed endpoints. We can use any of the convergence tests from earlier to determine whether an endpoint should or should not be included. And we find the radius of convergence, we use the ratio test. So from back in 9.6, 9.5, whatever the section of ratio test was. Okay? So let's get into the first example here. First example, we know that because this x here is not x minus c to some power of n, this technically c is 0, so we know that this value here is centered at 0. Centered at x equals 0. All right, good. Now what? Well, here's how we do this. Again, we find and we use the ratio test. So the ratio test, okay, is what we have to do is this. So we find a limit as n approaches infinity of the absolute value of the next n plus 1 value, right? So this is going to be n plus 1 factorial times x to the n plus 1 over 1 times, okay, so we multiply by that, and then we are going to multiply by the, I guess, the reciprocal is what we want to call it, okay, of the original function. So multiply by the original function 1 over that. So 1 over n factorial x to the n power. Okay, and that's an absolute value. Now what we want to do is we want to simplify that as much as we can. Okay, and so this is equal to the limit as n approaches infinity of, now remember factorials, okay, this is really n plus 1 times n minus 1 times n minus 2 and so on. And the same thing with this. This is n times n minus 1, n minus 2, n minus 3, and so on. So what's going to happen is these are actually going to cancel out. All right, so I'm going to be left with n plus 1 times x, which is equal, now if I plug in infinity, we know n plus 1 is going to go towards infinity times some variable x in the absolute value. So that means that this is actually going to go towards infinity. Okay? We know that infinity, okay, the number infinity is always greater than 1. So it's never less than 1. Like, that's never going to be less than 1. This is never true. Okay, never true. Thus the radius of convergence is equal to 0. Okay, and because the center is at 0, that means, right, if the radius of convergence is r equals 0, the series converges only at C. So that means the series converges, or only converges, at the center x equals 0. Okay, so that is what our answer is for the very, very first one. All right, hopefully that makes sense. Let's go to another one, and hopefully we'll, if that doesn't make sense, we can get some practice with the next one. So I'm going to delete, boom. All right, let's go to the next one. So again, we're going to use the same stuff as what we did. I'm just going to do this over here just for the room because this one is a little bit larger. So n approaches infinity of the absolute value of this to the n plus 1 power. Okay, so to the n plus 1 power. So negative 1, right, to the n plus 1. All right, times x to the 2 times n plus 1 plus 1, right? So 2 times n plus 1 plus 1 over 2 times n plus 1 plus 1 factorial times now the reciprocal of this one, okay, which is going to be negative 1 to the n, right, times, let's see, x to the 2n plus 1, and then 2n plus 1 factorial is going to be on top. All right, so there we go. Okay, cool. Okay, well, what's going to happen? Well, we know that this here and this here are going to cancel. Now, you're like, well, how does that make sense? I have an n plus 1 and an n. Okay, well, this here, okay, this here is actually going to be negative 1 to the n times negative 1 to the 1 power. And that's how I get negative 1 to the n plus 1. So the negative 1 to the n's are going to cancel. Okay, that means I'm left with a negative 1 inside. But because it's the absolute value, like I can just throw them away, cancel it out. Okay, that doesn't matter too much. So that goes away. I'm going to leave the absolute value there, but that goes away to make everything else look smaller. So now what do I got? Well, this is going to be simplified as the limit as n approaches infinity of the absolute value of x to the 2n plus 3 over 2n plus 3 factorial, all right, times 2n plus 1 factorial and x to the 2n plus 1. Now, how does this actually work? Okay, well, this here, okay, hopefully we can kind of understand this. I'm going to bring it over here to kind of show you here. This is really x to the 2n times x to the 3. And this here is x to the 2n times x to the 1. Right? So the x to the 2n's are going to cancel because I'm dividing. And then these can simplify, so that's just x squared. So that is going to simplify as just x squared while this goes away. All right? Now, how do I get the rest of it? Well, this is 2n plus 1 times 2n minus 1 and so on. This here is 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n dot dot dot. Well, this is 2n plus 1 times 2n minus 1 times dot dot dot. So that means that everything here is going to cancel with everything here. The only thing that is going to be left is this. That's how we got to make sure we understand factorials. All right, so I can rewrite this absolute value, okay, as the limit as n approaches infinity of the absolute value of x squared over 2n plus 3 times 2n plus 2 with absolute value. Well, we know that the numerator, right, is going to stay as x squared, but the denominator, when I plug in infinity, this is going to go towards infinity. Well, the higher the denominator goes, we know this is going to approach 0. And because 0 is less than the number 1, okay, because is less than the number 1, this is always true, okay, then we know that the r, the radius of convergence, is going to be equal to infinity. Therefore, also centered at 0, okay, centered at 0 because it's x minus 0 to the 2n plus 1, okay, centered at 0, so center is also equal to 0. And thus, the interval, okay, the interval that is going to actually tell me where it's going to converge, right, based on 3, because its convergence is infinity, that means it converges everywhere. So the interval is going to be negative infinity to infinity. So this is what I'm looking for right there. Okay, let's go on to the example number 2. I'm sorry, example number 3. Number 3. All right there. We got a lot of room on this one. Hopefully I can get everything written down on one side, but probably not. So I'll do number 3 first. Here we go. We can see that this here is centered. I can't spell. Centered at 2. Okay, the center is at x equals 2. Because it says x minus 2. Okay, so let's do the ratio test here. So we got the limit as n approaches infinity of the absolute value of the next term in the sequence. But in this case, right, I don't care about the negative ones, because when I flip those, they're going to cancel, and it's not going to make that big of a difference because it's an absolute value. Okay, so that doesn't matter. So I'm going to get rid of those. I'm not going to really take those into account when I do the rest of this. All right, so I get x minus 2 to the n plus 1 over, okay, n plus 1 times 2 to the n plus 1 times, now the reciprocal of this, right, is going to be x minus 2 to the n, and n times 2n is going to be on top, or 2 to the n on top. All right, now let's go ahead and do the math here and get some reducing of all this stuff. So this is going to equal the limit as n approaches infinity of the absolute value. All right, what's going to cancel here? This 2n is going to cancel with that, so I'm going to be left with just a 2 in the denominator. What else? I'm going to cancel this x minus 2 to the n and be left with just an x minus 2 up top. So I'm left with n times x minus 2 over n plus 1 times 2, or 2n plus 2. We'll say 2n plus 2. Okay, just to, I guess, show that there. We know that if we plug infinity in, right, because the powers, the n powers are the same exponent, okay, this is going to actually go to infinity over infinity. Now, the reason you're like, well, isn't it 1 over 2? Well, yes, but this x, we don't know what the value of that x is, okay? So that x could be anything, all right? So we don't know the value. So we know that if I plug infinity into the top, it's going to go towards infinity. And if I plug infinity into bottom, it's going to go towards infinity. So because I have infinity over infinity, okay, that's what we can do. And what do we do with this? We can use L'Hopital's rule, right? So let's use L'Hopital's rule. Technically, we could use like horizontal asymptotes, if you guys remember that, as kind of a way to do this if you forgot about L'Hopital's rule. But I'm showing you in case you remember L'Hopital's rule, and you could do that. If not, I'll show you horizontal asymptotes in a little bit. I know we don't know the value of x minus 2, but we can use that when we do the horizontal asymptotes. I'll show you here in a little bit. Okay, well, if I find the derivative, right, if I find the derivative with respect to n, right, I get x minus 2 over 2, okay, and the absolute value of that, right? So this is just going to be the absolute value of x minus 2 over 2. Because there's no n's to plug in, this is just a constant value, and so that's what I end up getting. We know that x minus 2 over 2 is going to be less than 1, or it has to be less than 1, okay? And so now what? Well, because it's absolute value, we got to remember what to do with absolute value. We basically say, okay, we split this into 2 equations. So x minus 2 over 2 has to be less than 1, and x minus 2 over 2 has to be greater than negative 1. Okay, we got to flip the sign and flip the number. That's how we do absolute value. So we have negative 1 is less than x minus 2 over 2, which is less than 1. When I solve this, I get x is less than 4, but greater than 0. Okay, x is less than 4, greater than 0. Now, if you remembered horizontal asymptotes because of the powers, this is a 1, this is a 1. Remember, we take the coefficient, so technically this is a coefficient. X minus 2 is some value. divided by the coefficient in your denominator. So that's how I get x minus 2 over 2. So that's just another way to think of it with horizontal asymptotes. All right. So now what? We know that the radius, okay, is 2. Okay, because if this value here was 3, this would only be 1 away, and this would be 3 away. So that's not the same. The radius has to be the same on both sides, right? So that's why the radius has to be 2. We know it's centered at 2, okay? And therefore, what we have to do now is we have to find the actual interval, okay? We have to find the interval. And in order to do this, we have to make sure we have to find the values at which 0 and 4, are they included or are they not included, right? Remember, if you go back to your second step, I'll show you up here. In the second scenario, right, the interval may have open or closed endpoints. So we know 0 to 4 is our interval, but I have to determine if 0 or 4 is going to be closed or not closed. We don't get that information from the absolute value pieces to find the interval. We have to do other things in order to determine if it's open or closed. So how do we determine that? Okay, so let me get rid of some other stuff up there so we can show you that piece. All right. Oh, that's not what I wanted to do. Let's do that. Okay. I wish I could just draw a circle and get rid of stuff back in Smart Notebook or whatever, on so old smart boards. All right. So here's what we're going to do. We're going to take this function. Okay, we're going to take this function and we're going to make x to be 0, right? Our first value of our interval. Okay, and this will help us determine if this is included or not included. Okay, so I'm going to say, okay, I have the sum from n equals 0 to infinity of -1 to the n plus 1, right, over, well, actually times 0 minus 2 to the n over n to the 2 to the n. Okay, let's figure out what we get here. So I got, let's kind of simplify it a little bit. N equals 0 to infinity. This is still -1 to the n plus 1. This is now -2 to the n over n times 2 to the n. All right. Well, what I can do here is break this down. Okay, so this is the same as saying n equals 0 to infinity of -1 to the n plus 1. This is saying, well, it's -1 to the n times positive 2 to the n, okay, times n times 2 to the n, right? So that means those can actually cancel. All right, those can actually cancel. And so I get n equals 0 to infinity. So now let's simplify a little bit more. Let's look at it. All right, these are going to cancel. Okay, if I have -1 to the n plus 1, so -1 to the n times -1 to the 1 times -1 to the n. So this is -1 to the 2n times -1 to the 1. Well, -1 to the 2n, no matter what n is, this is always going to be a positive value. So it's just -1 to the 1 over n. Okay? So this right here is going to diverge according to the p-series test. By the p-series test. So because it's going to diverge, that means that Z0 is not going to be included. Okay, so now let's do x equals 4. We're still on the same problem. All right, again, this is a lot of work here. This is what sucks about these series, man. I'm telling you, not very good. So we got -1 to the n plus 1 times 4 minus 2 to the n divided by n to the 2 to the n. So in this case, right, 4 minus 2 is just 2. I'm trying to delete here. That's just 2, right? So that means that's going to cancel. Okay, so this is what we're getting here is n equals 0 to infinity. We're getting -1 to the n plus 1. All of that is over n. What's going to happen here okay, this is going to converge because of the alternating series test. So because this converges, this diverges, that means the interval of convergence is going to be from this right here, this interval right here. 0 to 4, 0 not included, 4 included. Okay? So whenever something diverges, it's not included. Whenever something converges, it is included. Okay? All right, let's go to the last one, number 4, and then we'll call it a day. All right. Ugh, a lot of talking. I'm sorry. These are just long problems. Sorry. Let's start over here. All right. So let's do this by the ratio test, right? So we have the limit as n approaches infinity of the absolute value of. Oh, this is also centered at 3, right? Because it's x minus 3. So we got to make sure we know it's centered at 3. So I got to do the n plus 1. Right, plus that. So this is going to be x minus 3 to the n plus 1, which is going to be n plus 2, over n plus 1, which is just still n plus 2, okay, times 4 to the n plus 1, which is just n plus 2, times now the reciprocal of all of this mess. So I got n plus 1 times 4 to the n plus 1 over x minus 3 to the n plus 1, absolute valued. All right. Now let's simplify all this garbage here. I got the limit as n approaches infinity, okay, of the absolute value. Let's see. So x minus 3 to the n plus 2 and x minus 3 to the n plus 1, that's just going to, because the numerator is bigger, that's just going to leave an x minus 3 in the numerator. All right. N plus 1. And let's see, a 4n plus 1. That is going to be simplified to leaving it as a 4 in my denominator, and then this is going to go away. The n plus 2 and the n plus 1 I can't do anything with right now. So we're going to have to leave that as that, okay? So I got x minus 3 times n plus 1 all over 4 times n plus 2, absolute value. Hopefully you can see now, if you're looking at this as, from the last example, we talked about L'Hopital's rule, right? Because this technically goes to infinity over infinity, but because if we remember from horizontal asymptotes that this is going to mimic horizontal asymptotes, right? So this is actually going to be the absolute value of x minus 3 over 4. All right, now I don't want to show you the rest of that work because it takes time, but you can take the derivative of the top with respect to n, and you're going to get the same thing. This has to be less than 1, which, again, if you remember, in order to get rid of the absolute values, this is going to be that. We're basically doing that, okay? Solving it, you end up getting -1 is less than x, which is less than 7. So -1 is less than x, which is less than 7. So this is what our interval, we're going to use these values to determine if this is -1 going to be closed or open and 7 is going to be open or closed. So now let's plug them into the original series here. Okay, let's do that. So when x is equal to -1, okay, we get n equals 0 to infinity, right? We get -1 minus 3. So I'm just going to do a little bit of math. So that's -4, right, to the n plus 1 all over n plus 1 to the times 4 to the n plus 1. Okay, let's see what happens there. So what is going to happen? Well, if we think about it and if we recall from our simplifying, I don't know, in Algebra 2 or something, okay, this here, right here, because the n plus 1s are the same power, I can kind of split it up that way. Well, -4 over 4 is just 1, so that's just 1 to the n plus 1 over n plus 1. Okay? Well, this also, I'm sorry, negative 1, because right, negative 4 divided by 4 is negative 1. So this is going to converge because of the alternating series test. Okay, so that means it converges. Therefore, this 1, negative 1 here, sorry, is going to be an equal, right? So I know that no matter what, this is going to be negative 1 comma something. Okay, now I got to find it out with x is equal to positive 7. So now let's do the math for positive 7. Okay, so I get 7 minus 3 is 4. This is 4 to the n plus 1 all over n plus 1 to the 4 times 4 to the n plus 1. Those are going to cancel. So this is equal to the sum from n equals 0 to infinity of 1 over n plus 1. This is going to diverge because of the p-series test. P-series test. Okay, so this is going to diverge because of the p-series test. Therefore, the 7 is not going to be included, and thus your radius of convergence is negative 1 included to 7 not included. Okay, now this p-series, technically we're using p-series, but we're also using a limit comparison. Okay, so we're using a function that is comparatively similar to 1 over n plus 1, and thus using then the p-series to determine that it is not convergent. All right, and that's what we're doing right there. Okay, so there's our answer for 1, 2, 3, and 4, and this video is done. So deuces.